In chapter 10, we saw that we can take quotients of any functions, f of x over g of x, and we looked at a couple that were polynomials on top and bottom, and we even talked a little bit about factoring those. So in this chapter, we're going to focus specifically on those quotients which are polynomials on top and on bottom, and we call those rational expressions. So a rational expression is any expression that can be written in the form p of x over q of x, where p of x and q of x are both polynomials, and q of x is not equal to 0, since we know that the denominator can't be equal to 0. So some examples of rational expressions. Again, anything that's a polynomial in the top and in the bottom, so like x squared plus 5x over x cubed plus 2x plus 1. That would be a rational expression. Note that constants are also polynomials, so it could be something like 4 over x squared plus 3x. That's still a rational expression, even though there's no x's in the numerator. And like we already said, that the denominator can never be 0, so for any values of x that make the denominator 0, we say that the expression is undefined. Those are the bad points in the domain, so we've talked about how those are domain restrictions. So, for example, given a rational expression, we can find those values of x that make the expression undefined. You will have some questions like this on Hawks, where it's just asking you to find the values that make the expression undefined and not do anything else with it. So in this case, our denominator is just 2x minus 5, and so this will be undefined, where 2x minus 5 equals 0. So where 2x equals 5, and then divide by 2, and we get x equals 5 halves. So there's only one value that makes this rational expression undefined. Alright, part B. Now notice that we have an x squared, and so when we have x squared or x cubed or any higher powers, and we're looking for where the denominator is undefined, we need to try to factor. So if we have x squared plus 3x equal to 0, we factor and get x times x plus 3 equals 0. And then this gives us 2 points where it's undefined. So thinking back to when we solved equations like this in chapter 7, the x in the front gives us a solution of x equals 0. The x plus 3, if we set that equal to 0, we get x equals negative 3. So the 2 places where this are undefined are x equals 0 and x equals negative 3. And if you plug those into the rational expression, you will get 0 in the denominator, which again is a bad point. Okay, part C, another one where we need to factor. Okay, and notice that for undefined, we are only paying attention to the denominator. We don't care what the numerator is. We're just looking for where is the denominator equal to 0. Factor this and you will get x minus 3 times x minus 3 equals 0. And this only gives us one solution because they are both the same factor. And so we get x equals 3 is the only place where this denominator is undefined. Okay, so once we have figured out where our rational expressions are defined or undefined, then we can start doing some operations with these. And so let's define some of these things. These are the rules for rational expressions, which are really just the same as the rules for fractions. And so if we have a over b is a fraction or rational expression, we have something called the fundamental principle, which says that if I have a times c over b times c, then I can cancel out the c if it's the same in the top and bottom, and I just get a over b. Okay, so with numbers, that's what we just typically think of as reducing. With rational expressions, we will have to factor and then see if we have any factors that cancel. So the c in this case would be a factor. Reciprocals, so we have talked about reciprocals a little bit before, but a over b, the reciprocal of that, we just take the fraction and flip it, and so we get b over a. And if we take a over b times b over a, those reciprocals are always going to give us 1. And so that's kind of the math definition of how we define what a reciprocal is. Third, multiplication. If we have two fractions, or again two rational expressions, a over b times c over d, then we're just going to multiply straight across the top and straight across the bottom. So in the top we have ac, in the bottom we would have bd. So again, we've done all this previously at some point with numbers, and now we're going to take this and extend it to rational expressions. So we can multiply rational expressions or polynomials across the top and across the bottom. Division, hopefully you have learned how to divide fractions before. If we have a over b divided by c over d, we will keep the first fraction the way it is, so the a over b stays a over b. We change the division to a multiplication, and we flip the second fraction or take its reciprocal. So instead of c over d, now we'll have d over c. So we keep the first fraction, change the sign, and flip the second fraction, and then multiply to get ad over bc. And finally, for addition and subtraction, we know when we're adding and subtracting fractions, we need a common denominator. The same is true when we're working with rational expressions. So to add a over b plus c over d, we'll need to get a common denominator, often by cross-multiplying. And if we do, we'll have ad plus bc over bd. Okay, now we don't always need to cross-multiply to get a common denominator, and we'll talk about how to find the least common denominator for rational expressions in section 11.2. And here we want to make a note that BD should not be equal to 0, since that's our denominator. Okay, so for multiplying and dividing, you don't need to find a common denominator. For adding and subtracting, you do need to find a common denominator. This is the same as what we talked about for fractions, but now this is also true for rational expressions. Okay, so like I already mentioned, the fundamental principle can be used to simplify rational expressions, and a rational expression is said to be in simplest form if the numerator and the denominator have no factor in common. So when we practiced taking quotients of functions in chapter 10, we saw that we can only simplify those quotients if we can factor in the numerator and the denominator. So for example, maybe we have x squared plus 5x plus 6 over x squared plus 4x plus 3. We aren't able to reduce this until we are able to factor it. So in the top, this is going to factor into x plus 2, x plus 3. And in the bottom, we have x plus 1, x plus 3. And now that we've factored, we can look for any factors that cancel. So we see that we have an x plus 3 in the top and in the bottom. Those will cancel out. And we have x plus 2 over x plus 1. And this is our reduced form. Okay, now I want to make a note here that we're going to be factoring a lot of stuff in this chapter. And I'm going to do the factoring pretty quickly. Usually I'll just tell you what it factors into, so you need to review those factoring techniques and make sure that you're able to factor, because it plays an important role in all of the rest of what we're doing for this chapter. Okay, so let's look at some more examples of how we can reduce. In this first one, our factoring technique that we'll use is just factoring out a GCF in both of these. So in the top we can factor out a 3 and we have x plus 2. In the bottom we can factor out a 10 and we have x plus 2. And now we see that we have an x plus 2 in the top and in the bottom, and those cancel, and this reduces to just 3 over 10. And that is our final answer. Part B, notice that in the top we have an x cubed plus x squared plus 16x. So let's start by factoring out a GCF, and that'll give us x times x squared plus 8x plus 16. And then that one is going to factor more. In the bottom we can also factor out a GCF of x, and we have x times x plus 4. And then in the top we can factor again, so make sure that you keep your GCF, but then that factors into x plus 4 and x plus 4. Okay, either using the shortcut method or that's a special product. And in the bottom we have x times x plus 4. Now we look for factors that we have in common in the top and bottom. So we have an x in the top and bottom that can cancel. And we have an x plus 4 in the top and bottom that can cancel. And all we're left with is an x plus 4 on the top. And so we can just write that as x plus 4. You could write it as x plus 4 over 1 if you wanted to, but that's unnecessary. You can just write it as x plus 4 and leave it as that. All right, part C. These are some of our special factoring techniques. So these are ones that you may want to review since we haven't used them probably since chapter 7. So x cubed plus 125, that is a sum of cubes, and this is going to factor into x plus 5 and x squared minus 5x plus 25. Again, you might want to review the formula for that. In the bottom, we have a difference of squares, x squared minus 25, just factors into x minus 5, x plus 5. And now we look for any common factors. So we have in the top an x plus 5 and in the bottom an x plus 5, so those will cancel. Notice that they don't have to be right on top of each other to cancel. You can cancel them anywhere because we're multiplying across the numerator and denominator. And once those cancel, we're just left with x squared minus 5x plus 25. Remember, again, from chapter 7, that trinomial that comes from a sum or difference of cubes will not factor, so we don't even have to try. And in the bottom, just an x minus 5. And finally, part D. Here again, the only thing that we can do is a greatest common factor. So in the top, our greatest common factor would be 4, and we have x minus 3. Now in the bottom, that 3 minus x, we're not really used to seeing our binomials written that way. We typically have the x term first, and so we could write that as negative x plus 3. Or a trick that we are going to want to use, especially with these rational expressions, is to factor out a negative 1. So if I factor out a negative 1, then that just switches the order of my binomial, and now I have x minus 3. Okay, and to see why that's the case, let's start with 3 minus x. That's the same as saying negative x plus 3. So if I factor a negative out of that, then a negative x divided by negative 1 gives me a positive x, and a positive 3 divided by negative 1 gives me a negative 3. And so that becomes x minus 3 like we have in our rational expression. Now we have x minus 3 on top, x minus 3 on bottom, and we have 4 over negative 1, which we could just write as negative 4. Okay, this example, like I said, is something that we're going to do a lot, and so we give it a name. So in this case, in order to get factors that would cancel, we needed to factor out a negative. Specifically, in that example, we just factored out a negative 1. You might factor out a negative 2 or a negative 5 or some other number. But when we want to switch the order like that, we can say that our factors are opposites. So the factor x minus 3 and 3 minus x are called opposites. Okay, notice that they have the same parts to them, so they both have an x and a 3. They're both subtracting. The only thing that changes is the order that we're subtracting. We're doing x minus 3 versus 3 minus x. So those are called opposites. Don't get those confused with conjugates, which is where you change the sign. Here you're changing the order and keeping them both subtraction. So in order to cancel opposites, all we need to do is factor a negative 1. We can either factor it out of the top or the bottom. Normally we're going to want to do it in a way so that we have that form that we like where it's x minus something. So if we have x minus a over a minus x, we could factor out a negative 1 in the bottom to make factors that cancel. Or you could factor out from the beginning, you could have factored out a negative 1 in the top, and that would give you negative 1 a minus x over a minus x. And so you can see either way, we get factors that cancel. Either we cancel an x minus a or an a minus x. And when we have opposites in the numerator and denominator, we'll end up with a result of negative 1. Okay, so this is something that you want to be looking for. Most of the time when you factor, you'll see factors that can cancel right away, but you want to be aware that there's a possibility that there are opposites in there that we need to factor out a negative. Sometimes it'll be obvious that we should factor out a negative, sometimes it won't be quite as obvious. Say, part A, here's a pretty basic example. These are obviously opposites, x minus 6 over 6 minus x. So let's just take a negative 1. Again, I like to take it out of whichever one is going to make this more like the form that I'm used to. So I'll take a negative 1 out of the bottom, and that gives me x minus 6. Now I have an x minus 6 in the top and in the bottom that I can cancel. That would leave me with 1 over negative 1, which is just negative 1. Okay, now it's pretty rare that you would see just these opposites exactly like that. A lot of times we're going to have to factor, and then the opposites will be part of the factoring. So here's an example where we're at least factoring out a GCF. So here we have 5x minus 30 in the top. I'll factor out a 5. And have x minus 6. And then in the bottom, I notice that these are in the opposite order of what I'm used to. So instead of an x minus something, it's something minus an x. And so I'm going to factor out a negative to flip that order. And I'll factor out a negative 2 since that's the GCF. So I factor out a negative 2, that flips the order and gives me x minus 6. Now I have a common factor in the top and bottom, and that's x minus 6. And it's just common practice that we'll put the negative in the top, so I'll write this as negative 5 halves instead of 5 over negative 2. On Hawks, it won't let you type the negative in the bottom. You can either put the negative in the numerator, or you can put the negative in front of the entire fraction, like this. And I don't think it matters either way on Hawks which way you put it. Okay, and then we could also have something like part C where we need to use some of our other factoring techniques. And so here, let's start with the top. The top one's pretty easy to factor. This is a difference of squares, and so we'll have x minus 4, x plus 4. And then in the bottom, if you see something like this where you have a negative x squared, the strategy that I would suggest is just start by factoring out a negative 1. and then see what you can factor from there. So we'll take a negative 1 out, and that gives us positive x squared minus 9x plus 20. So that changed all of our signs. And now we can factor that trinomial that's in the parentheses. It's a little bit easier to factor when we have a positive coefficient for the x squared instead of a negative. And we may have talked about that in chapter 7. I can't remember if we did or not. Okay, so in the top we have x minus 4, x plus 4. And then in the bottom we can use the shortcut method. We just need two numbers that multiply to 20, add to negative 9, and those would be negative 4 and negative 5. So our factors are x minus 4, x minus 5. Now we look for factors that cancel, and I can cancel this x minus 4. And I'm left with a negative. I'll put my negative in front. Negative x plus 4 over x minus 5. I would recommend in this section putting the negative in front of the fraction instead of in the numerator, because if it's in the numerator then you actually need to distribute it or leave the parentheses. If you just put it in front of the fraction, you don't really have to worry about that as much. That's just making the whole fraction negative. So that's what I would recommend, is just go ahead and put the negative completely in front of the fraction as opposed to in the numerator or in the denominator. Okay, now we've been factoring a lot of these, but just a warning just to show you, when we are reducing rational expressions, we absolutely have to factor before we try to cancel things out. So we can't take something like 4x plus 8 over 4 and just cancel the 8 and the 4, since they're both constants, and say that that's 4x plus 2. Okay, this is the wrong way to do it, because then we've left out the fact that we have this 4x in the front. So you can think about anytime you have a plus or a minus, it's like those terms are attached to each other and you can't cancel anything from one of them without canceling it from the other. Another way to remind yourself of this is anytime that you have a factor like 4x plus 8, you can put parentheses around it, and that may make you less likely to try to cancel incorrectly. So the correct way to do this then, if we have 4x plus 8 over 4, is to factor out a common denominator in the top, and that would be 4. And then we have x plus 2 over 4. And now that we've factored, we can cancel out this 4 that's in front with the 4 that's in the bottom, and we get x plus 2. And this is the right way to do it. Okay, and if you don't see why that's true, you may want to just plug in some numbers and see what happens. See if 4x plus 8 over 4 is actually equal to x plus 2, and maybe that will convince you that that's the way that we need to go about it. Okay, so just a reminder that that's what you need to do. This will become even more important once we start moving on to actually performing operations on these. So we'll start with multiplication. Okay, so hopefully at this point you are comfortable working with single rational expressions. If not, you can go back and watch the beginning of this video over again, or of course feel free to come by and ask me and we'll work on it together. But now that you should be comfortable with that, we'll start actually doing arithmetic on these. We'll start with multiplication and division, because again, those are the operations that don't need a common denominator. So here are the steps for multiplying. I recommend that when you are multiplying, you factor first. So factor numerator and denominator, then multiply everything across while it's still factored, and then cancel any common factors that you have. So the reason I recommend doing it this way is because otherwise you have really long multiplications you need to perform, and then really long factoring to perform. If you do it this way, if you start by factoring and then cancel, it'll make all of those steps a little bit easier. So here's an example. Step 1 is to factor each numerator and denominator, And so in the first fraction we have here, x over x plus 6, nothing there factors, so we'll just leave that the way it is. And then in our second fraction, we know x squared minus 36 factors into x minus 6, x plus 6 over 5x. So now that we have factored both the top and the bottom, we can do the second step, which is to multiply straight across. And so if we multiply together everything in our numerators, we'll have x times x minus 6 times x plus 6. And notice again that I'm keeping everything in the factored form. And in the denominator, I'm going to go ahead and write that 5x in the front, and then I'll put parentheses around my x plus 6. So now I have a single rational expression that I've multiplied these two fractions together. Then step 3 is to cancel any common factors. So one common factor that I have is x plus 6. The other common factor that I have is this x. And I'm left with x minus 6 over 5. Okay, now one quick comment here is that you can cancel your factors before you multiply everything together. There's no reason that it needs to be a single fraction before you cancel. If you notice before you multiply them together that maybe the x plus 6's cancel, then you can go ahead and do that before you multiply them. Steps 2 and 3, the order doesn't really matter. You can switch those up if you want to. All right, let's try another example. These ones take a little bit more work to factor. So like I said, I'm just going to go ahead and factor them for you. You should try to factor these on your own and make sure that you can do it. And if not, come and talk to me and we will practice some more factoring together. So our first fraction will factor into 7 times x plus 2 times x minus 3 over x minus 4 times x plus 1. And our second fraction factors into x minus 4, x plus 4, and in the bottom factor out a 14, and then we factor to get x plus 2, x plus 1. Okay, so that's a lot of work factoring those. We need to use a couple different techniques, and so again, if you're not comfortable with factoring, please come and talk to me. But from here, now we can look for things that factor or that cancel. So like I said, we can do that before we actually multiply it together. We're just looking for anything in the top of either fraction that cancels with anything in the bottom of either fraction. So in order to cancel, it has to be one on top and one on bottom. So for example, we have an x plus 2 in the top of the first fraction. They can cancel with the x plus 2 in the bottom of the second fraction. And we have an x minus 4 in the top of the second fraction. They can cancel with the x minus 4 in the bottom of the first fraction. And then our 7 and 14 will end up reducing to 1 over 2. And then we can multiply together anything that we have left. And that gives us x minus 3 times x plus 4 over 2 times x plus 1, x plus 1. So even though we had two x plus 1's, they didn't cancel because they were both in the bottom. So they actually both stay in the bottom, and you could write that as x plus 1 squared. Okay, so I don't care, again, which order you do this in. You can multiply and then cancel, or you can cancel and then multiply. That saves you a little bit of writing. But notice that it does get a little bit complicated once you start canceling things. It can get a little messy, so make sure that you don't miss anything when you're doing that. All right, one more example here of multiplying. In our first fraction, we can factor the top to give us x minus 5 x plus 8 over x plus 7. In the second fraction, we can factor out a 3 in the top, and that gives us x plus 7. And in the bottom, we can factor out a 3x squared to get 5 minus x. And now we look for things that cancel. Sometimes it's helpful to put parentheses around things that don't have parentheses, just to help us realize that they actually do cancel. So that x plus 7 cancels. The 3's in the top and bottom cancel. And with the way that we have it written, those are the only things that cancel. Now, notice that in the first fraction we have an x minus 5, and in the second fraction we have a 5 minus x. Remember that these are what we call opposites, and we can factor out a -1 from one of these so that they do cancel. So I'll go ahead and factor out a -1 again from the bottom of the second one, just so it looks like that nice form that we're used to. And I'm going to kind of multiply and consolidate this into one fraction as I do that. So we have x minus 5, x plus 8. That's all that's left in our numerator. In the bottom, I said I'm going to factor out a negative, so I'll put that in the front. And we have an x squared. And since I factored out that negative, my 5 minus x turns into x minus 5. And now I have factors that cancel. I have an x minus 5 on the top and an x minus 5 on the bottom. And I'll take that negative from the bottom, put it out in the front like I mentioned, and I have negative x plus 8 over x squared. And there's my final answer. Now notice that if you forgot to do the opposites and to factor out a negative and cancel, you're going to have a different answer, and it's not going to be completely simplified. So that's one thing that, especially as you get to the end of the problem, you might want to double check and make sure that you haven't missed any opposites or any negatives that you can factor out. In this one, it wasn't quite as obvious that there was a negative there that should be factored out as it is if we see the negative at the very beginning. Alright, now we have finished our section on multiplying rational expressions, and we're ready to move on to dividing rational expressions. Dividing is a very similar process. We should start by factoring each numerator and denominator, and this way we don't have to do any long multiplications. But then instead of multiplying across the top and bottom, we need to remember to flip the second fraction. So we'll take its reciprocal and then look for things that cancel in the numerator and the denominator. Other than that, it's the same process as multiplication. So let's start with an easy example. 2x over x minus 1, that one is not going to factor, but when we divide, we need to multiply by the reciprocal of the second fraction. So I'm going to go ahead and just take the reciprocal before I factor, and then I'll factor it. Alright, here we go, we'll fix that. Flip it, and we have x squared minus 1 over 4x squared. So here you can either factor and then flip it, you can flip it and then factor, or you can do them in the same step, which is how I'll do the rest of these, is just combine it into one step. Here I went ahead and flipped it first, just so that I get that out of the way and I don't forget to do that. So now we have 2x over x minus 1. I'll factor my second rational expression, and I get x minus 1, x plus 1 in the top, over 4x squared in the bottom, and now I'm ready to look for things that cancel. So I have an x minus 1 in the first fraction and an x minus 1 in the second fraction. My 2 and 4 will reduce to give me just a 2 in the denominator, and one of my x's cancel, so x over x squared is going to cancel and just leave me with an x. So now kind of parsing through everything that I have left here, I have an x plus 1 over 2x. And that's my final answer. Okay, so again, dividing is the same process as multiplying, except for that extra step of flipping the second fraction. So let's try another. Like I said, in the rest of these, I'm going to combine that step of flipping and factoring all at the same time. This makes it go a little bit quicker, and it also saves us some space on the paper. So our first fraction here factors into x minus 6, x plus 2 over 4 times x minus 5. Now I will flip my second fraction and factor it at the same time. So instead of dividing, it's multiplying. And then we have 4 times x plus 6. So that was 4x plus 24. I factored into 4 times x plus 6. And in the bottom, x squared plus 8x plus 12 factors into x plus 2 times x plus 6. And now I look for things that cancel. So I have an x plus 2 that cancels, I have a 4 that cancels, and I have an x plus 6 that cancels. And then I look through for everything I have left, and I have an x minus 6 left in the top, and x minus 5 left in the bottom. And there's my final answer. Again, be extra careful when you're doing these that you don't miss anything that's left over after you cross everything out. So if you want to use maybe a different colored pen to cross things out, or a highlighter or something like that, it makes it a little bit easier to see what's been crossed out and what's left. That's just something that you want to be careful of. You would hate to miss points because you just misread the problem that you have written down. All right, next example. Again, I'm going to flip and multiply, or sorry, flip and factor at the same time. And so our first fraction factors into x minus 1, x plus 9 over x plus 7. Our second fraction, I'm going to start, so I flip that, and then I'm just going to start by factoring a negative out of the bottom. So every time I do that, I do it as a separate step because it's really easy to make a mistake if you try to do that in your head. So I'm going to go ahead and write it out. I take the negative out, and I have x squared plus 6x minus 7, and now I'm going to factor that in another step. And so I have, in the first fraction, again I have x minus 1 times x plus 9 over x plus 7. And then my second fraction, I have negative 2, and now this factors into negative 1 times x minus 1 times x plus 7. Sorry, got a little squished there. Hope you can read that. Okay, now I look for things that cancel in the top and the bottom. I have an x minus 1 that cancels. My negative 2 over negative 1, those negatives are going to cancel and turn into positives. So I'll just have a positive 2. And then notice that my x plus 7s don't cancel because both of them are in the bottom. So in order for it to cancel, we have to have one in the top and one in the bottom. So what I'm left with in the top is my positive 2 and an x plus 9. And in the bottom, I have x plus 7 times x plus 7, or if you wanted, you could write that as x plus 7 squared. Now on Hawks, I don't think it'll let you write it as x plus 7 squared. You would have to write it out as x plus 7 times x plus 7, so keep that in mind. All right, and one last example of dividing. Again, I am going to flip my second fraction and factor all in the same step. So my first fraction, I can factor just the bottom here. So you can try and factor the top. It's not going to factor. There are no two numbers that multiply to 9 and add to 3. So that one is just going to stay x squared plus 3x plus 9. My denominator factors into x minus 3, x plus 3. In my second fraction, I multiply, flip the fraction so that x plus 3 goes in the top. And in the bottom, this is a difference of cubes, factors into x minus 3. and x squared plus 3x plus 9. Okay, and now we see why we had that in the first fraction. So looking for things that cancel, and x plus 3 cancels, and that x squared plus 3x plus 9 cancels. Again, the x minus 3 doesn't cancel because they're both in the bottom. So here we have a special case where everything in the top cancels, and so what we're left with in the top is a 1. So remember, we've seen this before, that when we cancel something from the top and bottom of a fraction, we have 1, not 0. So that's going to give us 1 in the top, and in the bottom we have x minus 3, or you might write that as x minus 3 squared. And that's our last example. In the next section, we will be looking at adding and subtracting rational expressions, and that's where we need to find a common denominator. So you should practice with this multiplying and dividing before we move on to the next idea, which is a little bit more complicated.